I'm Nakul, and I'm very excited to talk about our work on large network ultra-wideband localization. So let me begin by saying that localization is a mature field. In small environments like rooms or warehouses, it's largely solved, often with centimeter level accuracy. However, as we move to larger multi-floor buildings, the complexity increases. And systems often require more infrastructure like fixed anchors, visual tracking, etc., just to maintain the same localization accuracy and quality. But at city scale, with hundreds or even hundreds of thousands of mobile dynamic nodes, this localization is still an unsolved and open challenge. And existing systems rely heavily on dense infrastructure, and they simply do not scale naturally. They suffer from slow updates and struggle with the dynamic nature of large networks. So our work addresses exactly this challenge of building a fast, scalable, and infrastructure-free system that can seamlessly scale from all the way building level to city level networks. And the need for this is real and growing every day. Emerging applications like drone swarms coordinating in complex 3D spaces, fleets of household and warehouse robots operating together without any centralized control, and millions of smart devices connecting across cities, they are all demanding a scalable collaborative system. So in this system, I'll first walk you through the theoretical techniques and methods, and then we'll come back and tie it with the physical layer and hardware like ultra-wideband radios in implementing this system. Now, most of the existing collaborative approaches, they use a graph-based method where we take pairwise range measurements and then stitch them to create a topology, a network topology. So let's say there are some nodes that can measure ranges with each other by exchanging signals and timing the responses back. We can take these measurements and create a distance matrix. And the core idea here is simple, that given noisy ranges in this distance matrix, we want to estimate the topology that best matches these measurements. So we formulate this as an optimization problem where we minimize the sum of this measured ranges minus the topology ranges that are computed from the estimated coordinates itself. And this optimization framework then gives us the coordinates, and this technique is quite popular. It's known as multidimensional scaling, or MDS in short, and it has been the foundation for any graph-based localization for almost 2 to 3 decades now. However, we see that as the network grows and scales, there are 3 key challenges that surface on the top. The first is ambiguities and measurement density. So imagine that one node in your graph only has 2 neighbors. Now, without enough constraints, it could be located in multiple places at the same time without violating any constraint. And it's only when we add this extra measurement, this extra constraint, is when this ambiguity is removed and we get back to a unique rigid topology. And the problem is that achieving this rigidity requires at least 3n minus 4 good neighbors in 3D and 2n minus 3 neighbors in 2D, which is a problem. Because in indoors at small scale, getting these neighbors is manageable, but in larger, sparser networks, it becomes a real challenge. And devices do have only intermittent or sparse connection, which makes it hard to collect enough measurements in various applications. Now, the second challenge is missing orientation. That means even if nodes know how far apart they are from others, they still don't know the direction or orientation. And inertial sensors can only give us a rough estimate, but they drift over time and they aren't reliable across hops and networks. So for emerging applications, especially in robotics, it's often required to have full 6 degrees of freedom pose, which has both 3D orientation and 3D locations. And the third and the most important challenge is the scalability, which is that as network grows, so does the number of measurements needed to maintain rigidity. And each measurement involves communication, which is finite time. And as it gets bigger, this communication overhead grows rapidly. And range-only methods, the ranging-based methods, they shoot out of control, making it almost impractical. So today, I'd like to present Locate 3D, a system that can scale from large networks to large networks while recovering full 3D positions and orientations, and it reduces measurement overhead by up to 75%, which is 4.2 times faster than traditional range-only systems. And at the core of Locate 3D system, there are 4 key ideas, and I'll present each of them. The first one is joint range and angle optimization. So, as I mentioned, the traditional system focuses only on minimizing the stress between these ranges, right? The measured and estimated ranges. But what we see is that modern devices, especially ultra-wideband radios, have started coming up with antenna arrays that not just measure distances, they can also measure the angle of arrival, right? And it uses the same signal exchange to get both of these information. But the classical MDS we saw does not support the use of this extra angular information. So in Locate 3D, this is our first idea, we capture both and jointly optimize over both range and angle together. And this extra angle, since it comes from the same exchange, does not need any extra time. And now each peer-to-peer measurement now becomes far more informative. And here we show that this significantly reduces the measurement overhead by 4 times without sacrificing any localization accuracy compared to the traditional range-based systems. And now that each measurement carries much stronger information, the next question is, how do we choose the best set of edges to actually localize this network efficiently? And to solve this, we construct a minimum spanning tree where we pick only a small subset of edges enough to localize this network. However, not all spanning trees are equal, and here we show a histogram of the errors across random spanning trees we pick in a graph, and we see that most of these graphs perform poorly. So we can't just pick edges randomly, and we need to be much more careful in selecting which links to include in optimization. And the reason for this is that the angle estimates that we got, they can be really noisy, especially due to the small aperture of the devices they are fit in, and also due to factors like occlusions, reflections, and non-line of sight paths. So we assign weights to these edges based on the measurement quality, where we factor in the angle confidence and non-line of sight detection. And now, instead of just minimizing the edges, we get an optimal selection of the tree that gives the same accuracy and same localization performance. But let's take a step back and ask that what if a spanning tree itself is not possible? And sometimes due to a missing constraint, we cannot guarantee a unique topology. So in that case, we divide the graph in rigid subgraphs. Now rigidity at its core means that once you fix all the constraints, the shape of the graph cannot deform without violating these measurement constraints. It means that if a graph looks connected, it might not be fully rigid if some link, let's say, have missing angle information. And it is these incomplete constraints that can lead to unligid or these loose subclusters within the original graph. Now our key intuition is to find these subclusters, and it is to somehow identify the nodes that can only undergo these collective motions. What I mean by this is you can visualize, imagine you can pull a node in one of this cluster, and what we see is that all the nodes in the rigid subgraph move in the same direction in which you are pulling, but the loose cluster has an independent but collective motion of its own. And this idea of this independent collective motion is what enables us to identify and classify these small rigid subgraphs. Now, how we implement this in math is super interesting. Our first step is to quantify this rigidity somehow, so we build a rigidity matrix. And in this matrix, each column corresponds to a measurement constraint equation that we got. And the rows essentially capture how would other nodes move for a delta movement in one of the node that I pulled. So next, we perform an eigenanalysis of this rigidity matrix and get the vectors that correspond to the near zero eigenvalues. And these zero eigenvalues reveals all the possible motions that are possible in the graph without violating our constraints in the matrix. So if you see, for a complete rigid graph, the only 3 trivial motions that are possible are these global translation and the rotation motion, right? Otherwise, if we have any extra vectors, they require further decomposition and get more rigid subgraphs. Finally, the last one we do is reference frame alignment to get our orientations. And to recover orientation, we need to align each node from their local frame of reference to a global frame of reference. And to do that, suppose we have node 1 and 2, which are measuring their angle of arrival with each other. Ideally, both of these angles should follow this simple geometric constraint, which is a supplementary constraint, right? However, in practice, most of these nodes might be rotated by an unknown offset, and if we take these into account, this is what the corrected constraint equation becomes. So finally, we solve for orientations again as an optimization problem, and we treat these orientation offsets for all the network, and it all aligns into a global consistent 3D orientation. Of course, in 3D, we have to take care of roll, pitch, and yaw, and so on. Now, with all these system components in place, we went ahead and built a Locate 3D prototype, which are these nodes, and we've tested extensively in both the controlled setups in small scale, building scale, as well as try to create a simulation with large scale environments emulating city scale dynamics. So let me first start with how it performs in small scale. This is the CDF of localization error, and we see that it has a median error of 18 centimeters in 2D and 30 centimeters in 3D. We also compare our performance with vision-based systems, which are the more popular ones in small scale, and compare it in different lighting conditions to show that existing VIO-based method, visual odometry-based methods, they degrade in dark environments, but we are robust to it. The next is this building scale evaluation, and here we have 32 nodes across a 5-story building, and the users are walking with our nodes as they would naturally. And in this system, we see that it achieves a 3D median error of 0.86 meters, and it recovers full 3D orientations with just one link each with less than 5 degrees of error. And again, all of this is without using any fixed infrastructure in the building. Finally, to evaluate the performance at massive city scale networks, we create a simulator, and we use real world measurements that we capture in the building to mimic this and create it as real as possible. On the left, here is the distribution of 30, 60, and 100,000 nodes with just one anchor. And on the right, we show a wide area simulation that is actually based on the New York City's transit dataset. And with just 5 anchors, we can achieve a decimeter level accuracy. And it shows that Locate 3D can now propagate across massive urban environments with minimal fixed infrastructure. To quickly summarize what we presented today, the first is Locate 3D, which jointly optimizes over range and angle measurements, strengthening the peer-to-peer constraints. Second, we minimize overhead with optimal edge selection, reducing the required measurements by about 75%. Third, we guarantee uniqueness of the estimated topology even under partial connectivity. And fourth, we scale seamlessly to networks over 100,000 nodes, maintaining low measurement latency and decimeter level accuracy. Thank you for your attention, and I'm happy to take questions.